What we are going to talk about today is we're going to talk about motion from accelerations. Now, here's where we're going to start putting together all sorts of information. Stuff those of you who've taken high school physics or even AP physics have seen before. This is the part that's going to start to look a little bit familiar. Start to, not quite. I'm still going to have kind of a different way of looking at things. Those of you who haven't taken physics before, good news. You still don't have to memorize any equations. Okay? But what are we trying to do here? If you recall at the beginning of the term, after we got through all of the math review and stuff, I talked about motion. Position, velocity, displacement, acceleration. We then followed that up with the discussion which led us to Newton's second law. Net force equals mass times acceleration. Now we're going to start putting it all together. The first step is to take a look at what's going on with the particular object. What are the forces acting on the body? Once you figure out what the forces acting on the body are, you find the net force. That tells you the direction of all of the forces when they're all added up, and the magnitude. Then you take the mass of that body divided by the net force. That gives you the acceleration. That's what we did in the last class, was getting the acceleration from the forces. But now that you know the acceleration, we're still not done with our analysis. What else can we find out? Okay, well, more. We can find out how fast is the object moving at a certain period of time. How far has the object moved? Where is it going to end up? Back to my little example. If I'm going to throw a rocket at the moon, all I know is all I know is the force. All I know is the force that the engine is putting on the rocket. From there, I can figure out the acceleration. From the acceleration, I can figure out how the velocity changes over time. From how the velocity changes, I can figure out the position, and I can figure out how long it takes for me to throw a rocket at the moon. See where we're going here now. Okay, so let me do a quick recap. And we'll go ahead and do some more interesting problems here. So first off is velocity. Recall, if you will, and these definitions are kind of important because they're going to lead us to our method. Recall the definition of velocity, which is the change in position over a time interval. The change in position over a time interval. Well, that's easy enough to calculate. All we got to do is take delta V, or V bar, or average velocity V, is equal to delta x over delta t. Or to translate that, the final position minus the initial position divided by the time interval. Kind of like all those football games this past weekend, when you're trying to figure out how far the rushes went, right? Where's the line of scrimmage? Where did the guy fall down at? Take the difference, that gives you the change in position. Now, we can rewrite this equation. Oh, one more little detail. It's independent of the path. We don't care how the guy ran. We just care, where did he start? Where did they end up? It's independent of the path, and we can reorder the equation to say that the average velocity times time gives us the change in the position. Nothing you haven't seen before. In fact, I've kind of pounded this into your head in the first period, in the first section of the course. So far, so good? Now, since we have V times T, that gives us the area of a rectangle. And so that's why I say that the area under a velocity versus time graph gives us the change in position. That, of course, would assume that the velocity remains constant, because two numbers multiplied together giving us an area, well, that's got to be a rectangle, yes? Okay. Now, we can also look at acceleration. The definition of acceleration is the change in the velocity divided by the time interval. Change in the velocity divided by the time interval. I've said it before. I'll keep saying it again. Because once we do that, it's easy enough to write it as A is equal to delta V over delta T. Or, as I've written it out here, V minus V0 divided by delta T. Now, I've changed the terms a little bit. V is my velocity at any time. And V0 is my velocity at time 0. So it's my initial condition and final condition, if you will. Okay? I'll go back to VI and VF for the rest of this period. Okay. Again, it's independent of the path. We don't care how the velocity changes, speeds up quickly, then speeds up slowly. That sounds a little contradictory, doesn't it? Speeding up quickly and speeding up slowly. But you see where I'm going here. End result of this is we can reorder the equation, and again, we can find an area under the acceleration curve, under the acceleration versus time curve, to give us a times delta t equals delta v. The area underneath the acceleration graph would give us the change in the velocity. All good? With me here? Everything makes sense? Okay. Now, I have a problem for you, which I will put up using the plickers. I will be merciful in that I won't do the polling while I've got the video going. So let me get the plickers going here real quick. Okay. So, if a drag racer starts from rest and travels 400 meters in 7.25 seconds under constant acceleration, what is the velocity of the car when it crosses the finish line? Okay. Go ahead and discuss among yourselves, and we'll see where we go here. Okay, so did the polling, and let's see, what are the results? 15 of you say 55%, 55 meters per second. One of you says he can't tell. Okay, you're all wrong. Okay, now, let me guess. What you guys did was you took distance, or velocity equals distance divided by time. That gives you the average velocity. I'm not asking for average velocity. I'm asking for how fast is the car going when it crosses the finish line. Okay? Common mistake. Common mistake. So let's go ahead and work this procedure up, because I've actually got a couple of questions involved with this. Okay? I've got a couple of questions. I want to know what's the speed at 400 meters, and I want to know what's the average acceleration over 400 meters. Now, right now, you can't tell me the average acceleration because you don't know how fast it is, right? If you had used the 55 meters per second, you would have gotten the wrong acceleration. So let me give you a method. And again, you don't have to memorize any equations, right? The method is this. First, we're going to do the same stuff we've done beforehand, which is draw the picture and make our table of variables. Now, if you drew the picture, you would have seen immediately where you made your error. Because if you look on the picture, at position x equals 0 meters, the velocity is 0. And at the position x equals 400 meters, the velocity is some unknown final velocity, but that's what I'm looking for. You following along? The average velocity you found is the average velocity over the entire distance. X is 400 meters, initial velocity is 0 meters per second, time interval is 7.25 seconds. We don't know the final velocity and we don't know the acceleration. Okay, so we know the velocity is changing, so that means the definition of the acceleration come into play. We know that the position is changing, so the definition of the velocity could come into play. So let's take advantage of a tool we've used before, namely the graphs. Let's make a velocity versus time graph and an acceleration versus time graph. If we do that, we might be able to solve our problem. Okay? So let's start off with the velocity versus time graph. Draw the velocity versus time graph. What should the velocity versus time graph look like? Where's it going to start? It's going to start at the origin, because we know what's the initial velocity? 0. So it's going to start at the origin, and it's going to have a straight line because it's a constant acceleration. We're assuming a constant acceleration, by the way. It's going to be a straight line sloping up. Now, we know that at whatever the time interval delta t is, that the car is going to be traveling with a certain velocity vf. Okay? Thus given by that point at the end of the line. Okay, so far so good, right? Now, from our definition of velocity, v is equal to delta t over delta x. The average velocity is equal to the change in position divided by the time interval. We multiply the time interval by both sides, and we get average velocity times time gives us delta x. Now, I realize I've been saying this for the past 2 months, that the area under the velocity time graph gives us the acceleration. Now I actually have to prove it, okay? Because the problem is this. If we take 2 numbers and multiply them together and use that to represent an area, those 2 numbers have to represent the sides of a rectangle, don't they? And yet, what's the shape that's given by this graph? A triangle. So I have to now prove that a triangle will give us the answer we need. And here's how we're going to do this. I'm going to take a really, really small interval of time. How small? Call it 1/100 of a second. Say from 3 seconds to 3.01 seconds. Could we say that in that 1/100th of a second, the velocity has not changed? And when I mean has not changed, I mean has not changed significantly. Okay? And oh, by the way, if the answer is, but wait, the velocity has changed significantly, fine, I'll look at a smaller time interval. If I get to a sufficiently small time interval, the change in the velocity is going to be negligible. And thus we could say that in that time interval, the velocity would be constant. Does that make sense? Thus, in that time interval, that 3 seconds to 3.01 seconds, I would end up making a rectangle for my area. Does that make sense? Okay, because at that time interval, it's moving at a certain velocity. I don't know what it is, but I know it's at a certain velocity v. And so I've got the area underneath that rectangle right there, the area of that rectangle, excuse me, is going to tell me how far the car has traveled in that 1/100th of a second. So far, so good? So the area under the rectangle is how far the car has traveled in that 1/100th of a second. Now what do I do? What do you think? What am I trying to find? That's one of them, but what else am I trying to find? Final velocity, okay, which means what am I going to need to use? Well, what I mean is this. I've just got a sliver of area, right? So what can I do next in order to try to get the big picture, get the big area? Find another sliver. That's right. Go from 3.01 seconds to 3.02 seconds and get another distance traveled. Get another rectangle. And then go from 3.02 seconds to 3.03 seconds, and so on and so on and so on. In other words, take the time and break it up into a series of segments, finding the areas for each of those segments. Thus, all I need to do is just add up all of those slivers together. Does that make sense so far? Sounds like a lot of work, doesn't it? Well, good news. I don't have to do that much work. Because if I go and choose a small enough time interval, see what I end up getting, is I end up getting a bunch of rectangles that fit underneath that triangle, yes? Every time I make the time interval smaller, that's going to give me more rectangles. But doesn't that fill the triangle even better? So if I can make each of my rectangles infinitesimally sliver thin, a moment in time, and then add up all of those rectangles together, then what do I actually have? No, not the slope. The area of the triangle, yes. If I have the rectangles sufficiently thin and I have enough of them, I will have, for engineering purposes, down to 5 significant figures, or however accurate I want, or however precise I want, excuse me, I can have the area of that triangle. And now, do I need to calculate all those slivers? Oh, heck no. Now all I need to do is calculate the area of that triangle. Do you see what I mean? That's my proof. Those of you who have taken calculus, that's the integration. Those of you who, and the method I used, That's called Simpson's rule. Okay, so that means all I got to do is find the area of the triangle, and the area of the triangle is 1/2 base times height. What is the base of my triangle? The base of my triangle is my time interval, isn't it? What's the height of my triangle? Come on, guys, what's the height of this triangle? It's going to be the change in the velocity. Since my initial velocity is 0, then the height is going to be my final velocity. In other words, I can substitute base and height with the variables, so delta x equals 1/2 delta t times delta v. Now, you look at that and go, well, what's the big deal about that? Well, it's real simple, because then all I got to do is go there. Delta x equals 1/2 delta t times vf minus v0, yes? Now, what's v0? 0. The initial velocity is 0, so that goes away. Do I know the time? Yes. Do I know the distance? Yes. So all I got to do is do a little algebra. Vf is equal to twice delta x over delta t. Making sense now, guys? And so then all I've got to do now is substitute the numbers and come up with 110 meters per second, which is my final speed. Now, what's the acceleration? Well, now that you know the final speed, the acceleration is trivial, isn't it? Because from our definition of acceleration, we can make an acceleration versus time graph where a is a constant line going across. The area underneath that is going to be our average velocity. Or excuse me, it's going to be our change in velocity. So that means the area of that block is going to be 110 meters per second. Because that's what we figured out from the previous section, yes? Okay, so then all I need to do is plug in the numbers and get 110 meters per second minus 0 meters per second divided by 7.25 seconds. Gives us our acceleration of 15.2 meters per second squared. That's a nice kick in the pants, yes? Okay, a little bit of an aside. The acceleration versus time graph gives us the information we need, but if we take a look, the definition of acceleration also gives us the information we need, because we know the initial velocity, we know the final velocity, and we know the time interval. How many equations have we memorized so far? 2. Definition of, actually 3, you're right. Definition of displacement, definition of velocity, and definition of acceleration. That's the whole thing. We've been able to solve the problem by using the geometry and those equations in order to figure out other unknown pieces of information, right? So I'm going to give you another problem then. This is a very, very practical problem. You ready? You're now civil engineers. You're building a road, specifically a freeway. I want to know, if a car goes from 35 miles an hour to 60 miles an hour in 11 seconds, how far did it travel, and what is the average acceleration that the car undertook? Go ahead and work it out amongst yourselves there. Okay, so looking at your work, I see about half of you actually made diagrams. And I only saw one where the diagram was right. Here's what I'm talking about. We know our initial velocity, we know our final velocity, we know the time interval, we do not know the distance. Okay, so here's what we're going to do. First, from the acceleration, that's easy to figure out, isn't it? Right? We know the initial velocity, we know the final velocity, we know the time interval. We could just plug it in and come up with 1.02, excuse me, 1.02 meters per second squared. So that's easy. That's the easy one. What about the distance? Okay. The distance is this. First, we're going to draw a distance versus time diagram. Or, excuse me, a velocity versus time diagram. Now, a number of you didn't even draw the diagrams. So there's your first error, because you don't have the equations. You've only memorized 3 equations. You following along with me, guys? You've only memorized 3 equations. Now, having said that, you can still solve the problem, but there's one detail. What a lot of you did was you started your velocity graph at the origin. Don't. The reason why is because the vehicle is moving. This is a car going onto an on-ramp. It hits the on-ramp at 30 miles an hour. It leaves the on-ramp at 60 miles an hour. So it's going to be traveling at some speed. Still, the distance is the area underneath the velocity versus time graph. Well, we look at this and go, I have a little problem with this one. How am I going to solve this one? I don't have an equation which gives me the area of this particular shape. Good news, you don't need one. All you need to do is break it up into two blocks. One block is a rectangle, the other block is a triangle. This is why you need your table of knowns and unknowns, because now you can label your diagram. You can label delta t, well, that's an unknown number, isn't it? You don't know the time. Okay. Oh, excuse me, you do know the time. That's right, 11 seconds. Again, that's the reason why you look at the table of knowns and unknowns. So we know it's 11 seconds. We know V0 is going to be the 30 miles an hour. We know VF is going to be the 60 miles an hour. So we now have the bases and the heights of all of our shapes, don't we? Delta x1 is just V0 times delta t. Okay. Delta x2 is 1/2 t times V minus V0. That's where your error was. You got this triangle, you didn't get that rectangle. You see? So what I'm trying to get at, and so a final distance is going to be 234 meters. Does it make sense you're going to go from 30 to 60 in about 700 feet? 700, 800 feet, does that make sense? Sure does. So that's a reasonable answer there. Reasonable length for an on-ramp. Okay, a little bit of an aside. Let's interpret this a little bit. The rectangle, delta x1, that would be the distance you would travel if you didn't change your speed. And then the triangle, delta x2, that's the additional distance you travel while you change your speed. Everything make sense now, guys? Now you see why drawing the diagram helps out? Okay, let me give you another problem. Let's see if you can work this one out. An airplane touches down on a runway with an initial speed of 75 meters per second. It coasts at a constant speed for 1.5 seconds. If it has a braking acceleration of negative 2.5 meters per second squared, what is the total distance that the plane travels until it comes to a stop? Okay, go ahead and work that one out. This is another one of those kind of important questions to answer, because you want to make sure your braking distance is less than your runway distance. Won't work, but I'm trying to show you why we're using those equations. Okay? Here's what I'm talking about. First off, we're looking at two different motions. Did you take that into account? That we've got two motions going on? The first motion is when the airplane touches down and coasts, and then the second motion is when the airplane starts to brake. Now that's, when I'm talking about whenever we have a motion problem and the motion changes, and when I mean, I'm not talking about, let me rephrase that. A number of people have taken motion to be the same as velocity or motion to be the same as acceleration. They're not. Motion is just that, motion, moving. If the conditions of the moving change, then we've got to look at whole new conditions, whole new sets. So in the first part, the airplane touches down and then rolls a certain distance at a constant velocity. That's the first motion, constant velocity motion. Then the braking forces are applied, and the airplane starts to slow down with the acceleration in the opposite direction. Now, the airplane's going to travel a second distance while the braking has occurred. Because we have two different motions, we need two different tables of knowns and unknowns. The coasting motion, it has the velocity, the time interval, the distance is unknown. The braking motion, the initial velocity, the final velocity, the acceleration, the time interval is unknown, and the distance braked is unknown. Okay? All good so far? All right. So let's build a velocity versus time graph. So the velocity versus time graph is going to look like that. First, you're going to have the constant velocity motion. So that means you're going to have a horizontal line along the distance, along the velocity of v0. And then, when the braking occurs, then you have the slanting line, which is going straight down. So we have two intervals, t1 during the braking, or during the coasting, t2 during the braking. What are we trying to find? What's the problem asking for? Total distance traveled, right. So that means I need to find the total distance as the area underneath the lines. That means I need to figure out delta x1 and delta x2. I got to figure out those two distances. So far, so good? Everything makes sense? Good news, delta x1's easy, right? We know the height. That's the initial velocity. We know the base. That's the first time interval. Therefore, the distance is going to be about 113 meters. Okay, so far, so good. But how far does the airplane go until it breaks? Or while it breaks, I should say. Well, the equation for that, 1/2 base times height. Okay, which is going to be 1/2 Vf minus V0 times delta T2. But I don't know what delta T2 is. I don't know how long it takes to come to a stop. I don't have it in my table of knowns and unknowns. So far, so good? Okay, one little aside. Why do I have a negative minus sign in front of my equation? What is that? Is the area delta x2, is that positive or negative? Is that above the line or below the, is it above the x-axis or below the x-axis? It's above, which means I'm going to be adding that distance to the distance already traveled. Problem is, if I plug in Vf minus V0, Vf is 0, and V0 is 75, isn't it? That would give me a negative number, wouldn't it? So if I didn't have that minus sign there, I would have a negative distance. Well, that would mean my airplane's traveling backwards. And that's not the case. When you build these equations, make your equations reflect what you see on your graph. If the area is below the x-axis, then you would have a negative area. If the area is above the x-axis, you would have a positive area. So far, so good? So the problem we have now is, what is delta t? Well, this is where we have to actually use the acceleration versus time graph. We draw the acceleration versus time diagram, and here's what we come up with. First off, there's no acceleration in time interval t1, because you're coasting at that point. That's the 1.5 seconds that you're coasting. We do have an acceleration, the negative 2.5 meters per second squared, during the next time interval, which we do not know. We do not know that time interval, do we? But what's the area underneath an acceleration versus time graph give me? The change in the velocity. Do we know the change in velocity? Yes, we do. We know that the area underneath the line is the change in velocity, so that area right there is going to be negative 75 meters per second, because you're going from 75 meters per second to 0. So A times delta t equals Vf minus V0. Okay, but I need delta t, don't I? Well, that's easy. Now all I got to do is take Vf minus V0 divided by A, and that gives us the delta t, which means it takes 30 seconds to come to a stop. All good now? Do you see how we build the equations off of the geometry? We still don't have to memorize any equations. We're just building the equations off of the geometry. Now that we know delta t2, we can now go back to the equations that we had written already. Namely, we know that x1 is going to be about 113 meters. So what's x2? Well, it's going to be minus 1/2 Vf minus V0 times delta t2. Well, now we know what delta t2 is, don't we? We can now put that number in, negative 1/2 times 0 minus 75 meters per second times 30 seconds, and that gives us a distance of 1,125 meters. Yeah, but there's one more detail. That's the distance that I'm braking. I now have to find the total distance that it takes to come to a stop, which means I've got to add x1 and x2 together to come up with 1,240 meters. which means my airplane is going to need somewhere about 3/4 of a mile to come to a stop. And anybody who's flown into with a relatively small airplane, that's not that unrealistic. Okay, I believe Vaden Field down here has got a 6,000-foot runway. Okay, this translates to about 4,000 feet. So you're not even braking that hard, are you? Okay? All right. Any questions on all of this? Because you had the distance you had to coast, 113 meters, and then you add that to the distance that you're braking to get the 1,240 meters. Okay? That's the reason why we have the diagram. Okay, so you following along, guys? That you can get a lot of information based upon the diagrams. The velocity versus time diagram is the one that's really the most flexible, because the slope of the velocity versus time diagram is going to give you the acceleration, and the area under the velocity versus time graph is going to give you the change in position. Now, having said all of that, next step is we're going to go into constant acceleration equations, and we'll talk about this on Wednesday, which essentially is this. If we have the same conditions over and over again, we're going to be seeing the same graphs over and over and over again, which means we're going to start seeing the same equations over and over and over again. So it might not be a bad idea to cut out all the prep work and go straight to the equations if we recognize that that's the conditions the equations apply to. See where we're going with that, guys? This stuff is covered under homework number 5. Homework number 5 is going to be due on Friday. If I have no other questions, let's go ahead and call this a morning, and I will see you guys when I see you next.